Okay, our group's topic is the incorporation of coarse and fine-grained policies for high-performance caching. I will talk about the introduction and improvement. As we all know, cheap multiprocessor is widespread for today's high-performance applications, and on-chip shared last-level cache plays an essential role in power efficiency and reducing the off-chip bandwidth. Unluckily, the cache miss can make our program become slower and consume more energy. So, we have to come up with some solutions in order to make our performance become better. There are some ways. First of all, the methodology for updating the SHCT can be modified to treat cache hits and cache miss in more reasonable way. Also, a border range of RRPV can be used at insertion position to distinguish access patterns. Last, SHCT can be trained with different policies, which means it is possible to incorporate other advanced coarse-grained policies. In order to improve the performance, first, we can train SHCT with samples. The LRU stock is divided into two logical segments. When a cache line comes, the following algorithm is applied. Here is the code of the algorithm. Also, the SHCT entry is initialized with the middle value in the signature range and is increased only on the first reference of a line in order to weight cache hits and cache evictions. And here is the table of training policy. Also, we can enhance SHIP algorithm. Different from SHIP, which predicts all the cache lines with RRPV equals 2, except the line with distance reference interval given by RRPV equals 3. Our method learns from the reference pattern sufficiently and dynamically change the insertion position to retain useful lines for longer duration in the cache. And here is the table that enhances SHIP policy.
Okay, hi everybody, I'm Gary. So I will introduce the following part. I will introduce first is the third part, experimental methodology. Okay, so we will first use the 4-core processor that built with the same settings. We keep this as the same part and we test the 4 different mixed multi-program workloads. So we control the 4-core processor as the unchanged part, and we change the workload to see the difference. So we can see that there's the table of traits for the simulations. There's 16-week cache set and 1/8 of the total sets are randomly selected as samples. So we can see that in here the samples are totally randomly selected and all different. So there's another table here. So the overhead for a single SHCT is 6 kilobyte, and the metadata of the sample set take up extra 15 bytes per line, and the hardware overhead remaining at the sample level as SHIP algorithm. And there's the table. Okay, I will next introduce the results and how we analyze those results. So the way we analyze the results and the speed up is due to this form, these equations. The speed up is equal to IPC minus IPC LRU divided by the IPC. So what is IPC? IPC is instruction per cycle. We use this to measure the performance. IPC actually can indicate the measurement for SHIP or our algorithm, and also the worst algorithm IPC LRU indicates the cumulative IPC for LRU policy. Okay, so there's a graph which compare the two algorithms. So we can see here the graph here. Our algorithm show better performance than SHIP with average 4.30% speed up compared with 3.83 except for the limb quantum. Okay, so we can see that our algorithm is overall better than SHIP. And for the next graph here, we can see, let me move here. Okay, so there's another graph. There's 4 mix. For the first 2 mix, we can see that our algorithm have a better performance than SHIP on each call. But for the last mix 3 and mix 4, our algorithm have a slightly worse than SHIP performance, because we think the situation occurs due to that some reasons. Maybe it's because the SHIP is more adapted to the traits, such as the limb quantum on single core, and the random sampling for SHCT makes the results less robust. So that's the reason why we have a worse performance than SHIP. Okay, so for the last part, I will introduce the final conclusion that we have and we made. So first, SEG LRU and BIP are combined to train the SHCP, which not only retain the advantage of LRU for recency-friendly access, but also improve the SHIP to be trash-resistant and scale-resistant. Also, SHIP is optimized for dynamic RRPV at the insertion position according to historical access patterns. Catch hit and catch miss are traced equally to update the SHCP in a more reasonable way. So for the single core configuration, our algorithm is much more better than the SHIP. It have a 4.13% speed up, compared to the SHIP is only 3.83% speed up. And for the quadro core configuration, both SHIP and our algorithm, provide around like 10% more speed up over the LRU. Okay, that's pretty much everything our group have done, and thank you for your patience for our presentation. Thank you very much.